Hello and welcome back to Chemist Tea Time. For today's lesson, we will be continuing on with our discussion on gases and begin talking about gas mixtures. Up until now, we have only been dealing with pure gases with single species. As we have learned in previous lessons, the ideal gas law assumes that all gases behave identically and they do not exhibit intermolecular attractive or repulsive forces. As a result, ideal gas equation does not take into account the nature of gases, only the amount. With this in mind, let's suppose we have three gases that are all present in equal amounts at the same conditions. If we mix these together, what would be the total pressure of the mixture? Well, let's think this through. Pressure of a gas is dependent on how much gas is present. So, if we mix these gases together, the total pressure of the system should be the sum of pressure of the individual gases. This is known as Dalton's law of partial pressure, where the partial pressure is in reference to the individual gases present in a gas mixture. The law written mathematically is as follows. The total pressure is equal to the sum of all the partial pressures of gases in a gas mixture. Let's try calculating the partial pressure of a gas in a mixture. Imagine we have gas A and B in a container at a known temperature and volume. We can solve for the partial pressure of gas A by setting up the following expression. Pressure of gas A is equal to the moles of gas A times the gas constant times temperature, all divided by volume. As you can see, we can use the ideal gas law to solve for a partial pressure of a gas in a mixture. We can do the same thing to find the partial pressure of gas B. If we were to add these partial pressures together, we can determine the total pressure of our system. Now, one last thing to point out, in the ideal gas law equation, it will give you moles. This can be written as your total moles in your system. So in the previous example for gas A and B, if we added the moles of each gas together, this would be equal to the total number of moles in your system. I know this is a lot of information to soak in, so let's do an actual example where we are applying Dalton's law of partial pressures. Deep-sea divers must use special gas mixtures in their tanks rather than compressed air to avoid serious problems, most notably a condition called the bends. At depths of about 350 feet, divers are subject to a pressure of approximately 10 atmospheres. A typical gas cylinder used for such depths contains 51.2 grams of oxygen and 326.4 grams of helium. The tank also has a volume of 10.0 liters. What is the partial pressure of each gas at 20 degrees Celsius, and what is the total pressure in the cylinder at this temperature? The first thing you should always do when approaching a problem is highlight or write out the information you're given and what you're looking for. In this example, they provided us with the mass of oxygen and helium along with the volume of the tank and temperature. They are also asking us to calculate the total pressure in the tank. They also gave us information that is not necessarily important to solving the question, which was the depth and pressure of the diver. Now that we have identified the important components of this problem, let's go ahead and approach this problem. We know we will be using the ideal gas law in order to determine the partial pressure for each gas. Let's go ahead and write out these equations. We are provided with temperature and volume, and they gave us a way to find the moles of oxygen and helium because they gave us the mass of each gas. We can use molar mass to convert grams to moles, which we end up with 81.54 moles of helium and 1.60 moles of oxygen. The next step is to plug the number of moles of each gas into the equation to determine the partial pressure of each gas. We end up calculating for helium 196.2 atmospheres and for oxygen 3.85 atmospheres. The next part of the problem asks us to determine the total pressure of the system, which is Dalton's law of partial pressures, and we just simply add them together and we end up calculating a total pressure of 200.1 atmospheres. Another way we can describe the composition of a gas mixture is using percentages, or more commonly referred to as a mole fraction, which is denoted by the Greek letter chi. This is simply the ratio of gas A in a gas mixture. The equation that you can use to calculate the mole fraction is by either dividing the moles of gas A by the total number of moles, or by taking the partial pressure of gas A divided by the total pressure of the system. These expressions can then be rearranged to the following, which states that the partial pressure of gas A, or the moles of gas A, is equal to the mole fraction multiplied by the total pressure, or total moles. Let's try practicing mole fractions. A 12.5-liter scuba diving tank contains a helium-oxygen gas mixture made up of 24.2 grams of helium and 4.32 grams of oxygen at 298 Kelvin. Calculate the mole fraction and partial pressure of each gas in the mixture, the total pressure of the system. Well, let's first identify what they gave us. They told us mass of each gas, volume, and temperature. We have two ways we can solve this problem. We can either determine partial pressure of each gas by using moles of each gas, or we can calculate the total number of moles to determine the total pressure and use mole fractions to calculate partial pressures of each gas. First off, let's calculate the number of moles for helium and oxygen. We can use molar mass to convert to moles of each gas. This equates to 6.05 moles of helium and 0.135 moles of oxygen. Next, let's calculate the mole fraction of each gas by using the equation. The mole fraction of helium calculates to be 0.97817, and for oxygen is 0.021827. We can calculate the total pressure by using the total moles of our system, which we get by adding moles of helium and moles of oxygen together, which equates to 6.185 moles. We can plug this in to the ideal gas equation, and the total pressure calculates to be 12.099 atmospheres. In order to find the partial pressure of helium and oxygen, we must multiply the total pressure by each mole fraction. The partial pressure for helium is 11.8 atmospheres, and for oxygen it is 0.264 atmospheres. It is important to review the concepts covered in this lesson and practice the problems. Thank you for joining me on Chemist Tea Time, and I will see you next time. Thank you.